so in the last class we had discussed the scattering theory in very brief, and then what we said is we can find a number density correlation function, and if I Fourier transform it, I get the structure function that we can get by scattering experiments. So now I will go further from that point and define what is known as the pair distribution function, and then we will derive expressions for the pair distribution function using the for the polymer chain, and then I will show how does the structure function will look like for the case of a polymer chain. Okay, so what we had discussed is the number density correlation function that is equal to if I Fourier transform this, I get the structure function, and actually what I have derived was I get something like n of q, n of minus q. And then I said that Fourier transform is easy to do, the inverse Fourier transform is non-trivial and can only be done for certain cases. So now I will define the pair distribution function we had already discussed what does the function look like for the case of a liquid, solid and a gas, but now I will basically derive in two steps. So I will first define it as the function g of two positions x1 and x2, that is the probability of finding a particle at x2 if a particle is at x1, and then I will explain when does it reduces to just one variable. Okay, so let us define the pair distribution function in this particular way. So this is my pair distribution function. So now it is similar to what we had, with the only difference that we exclude the alpha equal to alpha naught alpha prime case. So we exclude that, otherwise it is similar to the number density correlation function on the right hand side. So essentially I can write this as this minus whatever we get for alpha equal to alpha prime. So when alpha equal to alpha prime, we do get delta of x1 minus x alpha, delta of x2 minus x alpha, which we can write as delta of x1 minus x2 using the formula I have derived earlier in the class. And so I can write this as n of x1 we make sure that we have consistent dimensions across. So the first one is the number per unit volume multiplied by number per unit volume. So we have n square by v square here. We have number per unit volume, so it must have 1 by volume. So it is per unit volume square, number anyway is dimensionless. Okay. So, now G of x1 x2. So, I have already said earlier that the number density correlation function in some sense represents the probability of finding another molecule at x2 or another particle at x2 if one molecular particle is at x1. But there are two things here, the number density correlation is not normalized properly, and the second thing is that we do not exclude the case where two molecules occupy the same position. That of course is not possible in the case of molecules. So, G of x1 x2, the way we have now defined, when we exclude the case alpha not alpha equal to alpha prime, is the probability of finding a different particle at x2 if a particle is at x1. Okay, so the G x1 x2 is the probability of finding a different particle at x2 if a particle is at x1. So, there is a detail here that we do not really look at a particular position, but a small volume around that position, just to make sure that we cover the entire space. So, when I say at x2, it really means a small volume around x2, let us say something like x2 minus delta x by 2 to x2 plus delta x2 by 2, or we can say a small volume dx2, so that we can cover the entire space when we look at the probability. So, we can make two approximations here when we are looking at a homogeneous fluid. So, homogeneous fluid will have the same ensemble average density, that is, and we have discussed this for the case of liquid, this is ensemble average is simply n by v, which is a constant. And the second approximation is that we need not look at G of x1 x2, but we can look at G of x1 minus x2. What essentially it means is known as translational invariance that applies for homogeneous fluids, and the idea is that I do not need to look at every possible pairs of positions, but we can look at only distances between the two positions, right. So, let us say I start here and go here, and this distance is say x. I can start as well here and go here, as long as that distance is also x, the two pair distribution functions will be identical. Okay. So, if we have this and if we have that, then in that case we can talk in terms of G of x in place of, only when these two assumptions are met we can talk of G of x in place of G of x1 x2. Okay. So, now we can show, and I will not derive it, is just like the structure function I of q was the Fourier transform of the number density correlation function, in the same way the structure factor, which was an intensive measure. So, we divided the structure function by n or v to get the structure factor. The structure factor related to the Fourier transform of the pair distribution function. Again, pair distribution function is like a normalized version of the number density correlation function, just like the structure function factor is a normalized form of the structure function. So, the relation that I will not derive is I can write the structure factor as the following. So, for the homogeneous fluid, where this is the average number density. Now, if the fluid is also isotropic, then all the three directions are identical. So, in that case we can actually replace g of x as g of absolute value of x, which is typically referred as g of r and called the radial distribution function, which we have already shown for the case of the liquid and gas when we have been discussing the form of the pair distribution function. So, for the case of liquid and gas, we looked at absolute value of x along the x axis, and for the case of solid we chose to use the actual value of x, that is the vector value, just because the gas and the liquid is assumed to be isotropic. Okay. So, now let us see how this g of r scale in the case of a polymer solution. We will start with a polymer chain and think of it to be like a dilute solution. In that case, the statistics will be similar to what do we get for a polymer chain. Okay. So, we have derived, so for a polymer chain, in the dilute case, the number of segments at a distance r, that is what I called m, is given by r to the power 1 by nu, where nu will be the coefficient I get differently for the random walk, self avoiding walk and collapsed chain case. So, if I know the number of segments at a distance r from a given segment or bead, the number density that we see within the small volume there will give me a measure of the radial distribution function. Other way to say that is, let us say if I keep as central at center the particle which I want to keep as reference, and if I look at a volume r around it, we assume a sphere of volume r around it, and if I am interested in a number of particles present in that volume at the location r, that is we may be interested in a spherical cell that is between r minus delta r by 2 to r plus delta r by 2, or having a thickness delta r. So, if we look at the spherical cell that is at distance r, and we are looking at a cell of thickness delta r. So, as I said earlier that we are interested in a small volume at distance r. So, then the g of r would scale like the number density that is present inside this particular cell of thickness delta r, and that would then become the number of segments present in that volume that I represent using delta n r divided by the volume of that segment, which we can represent as 4 pi r square delta r. That will be true for small delta r values. If you want to be more rigorous, we can say it is 4 by 3 pi r plus delta r by 2 r plus delta r by 2 cubed minus r minus delta r by 2 cubed, and the leading term there will give me 4 pi r square delta r, where delta r is small. Okay, so I am using a small r here, so the idea remains the same. Okay, so now I can represent in the limit of delta r very small, I can write this as also 1 by 4 pi r square, the derivative dn by dr. So, this particular thing will scale like the n, that is the number present there in the spherical cell, by the total volume, which in this case will scale like n by r cubed in 3 dimensions, or if I am doing in general, then it is n by r to the power d, where d is the dimensionality. And we know what the n is scaling like. So, n is scaling like r to the power 1 by nu, and so essentially what do we get from here is g of r scaling like r to the power 1 by nu minus d. Okay. So, if I start from this particular relation we have derived, that is g of r is r to the power 1 by nu minus d. In fact, we associated 1 by nu to the fractal dimension df. So, we can equivalently write as g of r scales like r to the power df minus d. If I do a Fourier transform of this, and I will not derive it, what we get is s of q scales like qb to the power minus 1 by nu, or equivalently s of q scaling like qb to the power minus df. So, now again we can do it for different cases, because we know the new values corresponding to them. For example, if I am doing in 3 dimensions, then for theta solvent, when we have ideal chain, nu equal to 1 by 2, g of r will scales like r to the power 2 minus 3, that is minus 1, and s of q will scales like q to the power minus 2. In a good solvent, nu is 3 by 5. So, g of r will scale like r to the power minus 4 by 3, and s of q will scale like q to the power minus 5 by 3. In the bad solvent, when the chain is collapsed, we get nu equal to 1 by 3, g of r scaling like 1 and S of q scaling like q to the power minus 3. Okay. So, this tells me the behavior with q. Now, there is a point to note here that my q goes like 1 over lambda, and lambda sets the characteristic length scale that I am looking at. So, if I look at a smaller q value, it gives me the behavior at longer length scales. If I look at the larger q values, it gives me the behavior at smaller length scales. So, essentially when the length scale lambda become comparable to the chain radius, if you think of like what will happen there is it is no longer a fractal as soon as we look at length scales higher than the chain dimension, because the whole idea of self similarity and fractal nature will apply to segments of the chain, not the whole chain as a whole. Okay. So, whatever we have derived will be only true at length scales, that is R values significantly lower than the RG value. At larger length scales, we will have slightly different behavior that will not derive. So, in this way we have a systematic way starting from the fractal dimension of the polymer chain that we have derived in different condition. By Fourier transforming, we get what do we expect in the S of q, and as I have said earlier, S of q is the experimental output from the scattering experiments. So, we have a way to verify from experiment whether this scaling is observed or not in the particular case, or vice versa. By looking at the scattering plot, we can identify whether we are in a good solvent regime or a bad solvent regime or a theta solvent regime. Okay. So, this is like a way to look at the structure of the chain, and this adds to the size and shape characterization that we have discussed earlier. So, with this, now I want to take to another dimension of things, that is all these are like theoretical stuff, and for many cases that we have shown we can do very nice derivations, but we can also get these results and actually more results if I also employ simulations. In that case, we can actually see what the polymer chain looks like in different solvents, and we can have a more accurate way in a sense to get the scaling laws, because the simulations will not have some of the assumptions that the Flory theory made. For example, we assume that the concentration of segments are uniform, the interconnectivity of the segments were ignored for the purpose of interaction energy, and the elastic energy was taken for an ideal chain even though the chain was not ideal. So, if I do a simulation, we can relax those assumptions and try to get the scaling laws more accurately, and in fact, it turns out the simulations itself are not very difficult to perform. So, we already had discussed the simulations in the case of ideal chain earlier, where I said I can generate many conformations of a polymer chain, get there for example the end to end distance squared values, take an ensemble average over many conformations, and then we can get the scaling laws that we got by the theory. Now, I want to extend the idea to the cases where we do have an excluded volume interaction. Okay. So, simulations will perform can be of two types. The most common type in polymer literature is the Monte Carlo simulation, at least for the toy models we have been discussing, and then there are other simulations. The other class is molecular dynamics simulations. Actually, there are many other methods that have been developed either as some sort of extension of these two methods or methods of their own. So, I will discuss the Monte Carlo simulation and molecular dynamics simulations in somewhat more detail. So, I want to first give you again the idea of how the Monte Carlo simulation works, and then we will see how do we apply on a polymeric system. So, the basic idea of a Monte Carlo simulation is the following. We start with a configuration of system, that is, we start with the polymer chain. In fact, the Monte Carlo is a very general method. So, we can start with the polymer chain, we can start with any system that I am interested in, and the key idea is that we start with a simulation box that is representative of the entire system I am considering. So, for example, if in reality we have polymer chains contained in the beaker, the case I was telling you when I was discussing the effect of concentration. So, it is probably not worth it, and it is probably very expensive to do the simulations over the entire beaker. So, we will not do simulations over the entire beaker, we will do simulations over a smaller volume within the beaker that represents the condition in the beaker. Okay. So, the simulation box is not the same as the experimental container that you are using. Simulation box is something that represents the bulk behavior that you see in the experiment. So, for example, I can draw a small volume inside my beaker, and that volume will contain certain number of molecules and atoms, and we will simulate that in the simulation, and then we expect that whatever behavior we do get represents the behavior of the bulk. So, the first thing is the simulation box should be significantly large, that it is representative of what is going on in the system. At the same time, it cannot be very high, because if it is very high, then the simulation becomes computationally expensive. Okay. So, I will use the word representative of the bulk system. So, at least for the dilute concentrations, we can hope to simulate only one polymer chain in a small simulation box, and that will show the behavior that we have got for the scaling laws of polymer chains. If it is an entangled system or at high concentrations, maybe we need to take a larger volume considering more polymer chains. But at least for the dilute case, if I am interested in the scaling law for a single polymer chain, we can just make a simulation box that contain one chain in the system. So, let us say this is my simulation box, and we have a chain contained in there, and let us say I am representing the polymer chain using the bead spring model. Okay. So, we use the bead spring model. Now, if you recall from the flow-d theory, I represented the energy of the chain as sum of the elastic energy and the excluded volume energy. So, in this case, the elastic energy is because of the springs that connect the beads. So, I am assuming that between every adjacent bead in the polymer segment, we have a spring of certain spring constant k. For the Gaussian chain, we have derived that the spring constant chain of the spring goes like kBt, but in general we can keep a k value that is arbitrary for the simulation. So, it can either be written as in terms of extension x as half kx square, or we can write something like half k x minus x naught squared, where this becomes my equilibrium or average segment length. Okay. So, this takes care of the elastic part. So, now if you have, for example, n beads in the system, you will have n minus 1 springs, and we look at the spring energy of all those springs. That gives me the elastic energy. If I look at the interaction energy, now the interaction energy can be present between every pair of beads in the system, right. So, let us say if I look at a particular bead I here, this bead interacts with 1, 2, 3, 4, 5 until all the beads that we have in the system. So, we have to look at the interaction energy. If I am doing the idea that we only look at the two body interaction, then in that case it is sum over for bead I, it is sum over j equal to 1 to n, n being the number of beads, some u that represents the interaction between I and j. Okay. So, we can write some sort of pair interactions and that is way if I count all the pair interaction for a pairs containing that particle, we get the total energy due to interaction energy for that particular bead. So, if I sum that over all the beads, we get the total energy due to interaction in the system. So, u int is sum over I 1 to n I can write this as I equal to 1 to n, j equal to 1 to n, u int of I j. Okay. So, we have not yet said what that interaction energy form is, but we know that we have to sum over all the pairs in the system. In fact, to be precise, we have to exclude the cases where j is not equal to I, because there is no self interaction considered. The interaction energy only happen between two beads which are distinct. In fact, in many simulations it is preferable to also exclude the adjacent beads, that is we also do not want j to be equal to I minus 1 and j to be equal to I plus 1, because the interaction between adjacent beads are anyway captured using the spring force. Okay. But that depends on the model. The key idea is that we have to exclude the self interactions, and we may or may not exclude the interaction energy between the adjacent beads, where the interaction energy is only referring to the non-bonded interactions. The bonded is already considered in the first part. Okay. So, now the question is that how do I construct the form of this u int function, okay. And that is where there is a very famous potential that becomes very useful. It is known as the Lennard-Jones potential. One of the first applications of this potential was to explain the behavior of real gases. So, this already is something that can give you the van der Waal equation of a state. So, the potential works like this. So, I can look at the u int between a pair of particles at a distance r as a function of r. Now, this particular interaction should possess certain features. First of all, it should capture the range of interaction. So, this particular potential is already for short ranged van der Waals interactions. for example, we have van der Waal attractions, we know that it decays like r to the power minus 6. Now, the issue is this: if I just use this form, then at r equal to 0 we will have an infinite interaction energy. That will mean that all the beads will collapse into one. Okay. So, this goes against the idea that the beads will contain some amount of hard core that is giving rise to the self avoiding walk that we discussed in good solvent, or an excluded volume as we discussed in the Flory theory. So, what we typically also want is, we also want that at small distances there should be some repulsion which is referred as the hard core repulsion that prevents overlap of beads, because again if it is not present, then the overlap of beads give rise to very highly negative energy, and if I do such a simulation, I always go to one bead collapsing into, all the beads collapsing into one bead. Okay. There is no specific form for this particular potential. When I say no specific form, there is no physical basis of choosing what the hard core repulsion should be. In practice, it should be infinite at r equal to 0 and non-zero otherwise, but that is difficult to handle. So, it is preferable to have a very steep potential, and for the reasons we will see, it works better than having an infinite energy hard core at r equal to 0. So, then I can construct what is known as the Lennard-Jones interaction as so, in this particular expression, sigma is sort of a length scale. Sigma is the value at which the u interaction crosses 0. You can put in sigma equal to r here, and you can see it goes to 0. And then if I look at the depth of the potential, the depth is given by epsilon, and if I want to know where the minimum lies, I can do the minimization of u with respect to r, which gives me r star is 2 to the power 1/6 sigma, and this is where it happens. Okay. So, beyond the value of r star, we switch on the attractive van der Waal in this particular case. Below that, we have a steep potential which becomes positive for r less than sigma, which prevents the beads to overlap. Okay. So, now of course, the potential decays very rapidly, and at higher r values pretty much the potential is very small. So, we will come back to this point in a moment, but what we have so far is we have an elastic energy and we have a non-bonded interaction energy that is represented as a sum of the two body interactions, and we look at all the pairs in the system excluding self pairs. Okay. So, now the question is like, how do I incorporate that energy into the simulation? Okay. So, the way of doing this is in the Monte Carlo method is the following. We will first describe what the algorithm is, and then we will discuss like why does it work. So, the Monte Carlo algorithm is the following, and I am doing it for a polymer chain case again for a bead spring model, but the idea itself is very general, it can be applied for many cases. So, we start with a chain conformation and to begin with we do not know what the energy of conformation is right. So, we always start with a random conformation and which will have certain positions of the beads. Okay. So, let us say curly bracket R I indicates the positions of the bead, where the curly bracket is a shortcut for the positions R 1, R 2 to say R m. Okay, so now what we do? So now we do a trial displacement of a randomly chosen bead. So, I can pick any of the bead randomly from 1 to m, and I will displace as from R I to some R I prime. We will come to like how exactly we do the trial displacement, but let us say for the moment that we have chosen any particular bead randomly, and then we try to displace from R I to R I prime. Okay, so now the trick comes. So now we compute the change in total energy due to the trial move which is something like delta u, and this delta u is computed considering both the elastic energy, the bonded term, and the interaction energy that we treated using the Lennard-Jones interaction, which is for the new position if the trial is accepted minus the old position, where u includes both elastic and Lennard-Jones. Okay. So now we know that we have performed a trial and we have computed the energy change due to the move. So now here comes the main Monte Carlo logic, that ultimately what do we want? We want the system to go towards the lowest free energy conformation. So we should accept moves which are going to lower energies, and we should either reject the moves which are going to higher energy, or at least accept with a lower probability, because higher energy states are anyway not the ones that are present in equilibrium. So one of the standard method is we accept or reject the trial with some probability function, and we will discuss that in the next lecture. So we do accept and reject, and then we basically go to step 2 and continue until properties of interest converge. Okay. So, again, so the idea is that let us say I want to find the end to end distance squared of the chain. So, I will start with random configuration, I will do a trial displacement, I will accept or reject based on the energy change. So, we will have some probability to accept or reject based on energy change, and then I will continue doing the simulation until whatever property I am interested in converges to a value that we will call the equilibrium value of simulation. So, I will start from this particular point in the next class. Thank you.